Hi, my name is Bogdan and I'm a PhD student at Politehnica University of Timișoara, but this work would have not been possible if it weren't for RayScape, a medical imaging startup that I co-founded a few years back. I would like to present you some of our work in domain generalization, specifically in chest X-ray pathology classification. So far, studying generalization on X-rays has seen sparse advancements with little replicability. Prior works usually rely on emerging public datasets, which might be problematic. For instance, when we compare the seemingly similar labels of four well-known X-ray datasets with a set of consistent annotation of our own, the high degree of concept shift became evident. So how did we go about this? We started a large-scale data collection process with 23 partner hospitals and a team of radiologists annotating consistently 50,000 X-rays. That allowed us to build robust setups and isolate three little understood covariate shift factors. We started with exposure shifts. We've seen in practice that even similar hospitals with similar demographics and identical X-ray hardware still pose problems to our models. To isolate this phenomenon, we match all those factors and split the data into 9 domains, each representing different acquisition parameters. Next, we did the same, only this time the new 12 domains represented different device manufacturers, as they usually use proprietary technologies. Lastly, we use 5 different domains representing different geographical locations. The human anatomy and disease prevalence is known to vary with population. The results were concerning, to say the least. The out-of-distribution mean F1 of the 17 tested pathologies dropped significantly with each of the 3 factors. However, the worrying part was actually the pneumothorax generalization gap, which consistently took a hit with up to half of the F1 slashed when exposure was shifted. Pneumothorax being one of the clinically consequential pathologies, often fatal if not immediately intervened, did not make the situation better at all. So we proposed LISA-topK, which is a multi-label adaptation of Learning Invariant Selective Augmentation, also known as LISA. LISA is fundamentally a mix-up strategy applied selectively on samples with the same domain but different labels, and vice versa. The intra-domain strategy works just fine, but the intra-label does not translate well to multi-label use cases. So basically, finding pairs of patients having the exact same combination of all the 17 pathologies is statistically unlikely. So we propose doing the intra-label mix-up by matching only the top K most problematic classes, in this case K being 2. We put in context 2 of the few existing methods, which although help with exposure shift a bit, actually perform worse than the basic empirical risk minimization on the others. Original LISA did not translate well to the multi-label regimen and was substantially surpassed by LISA-topK. If there are any key points worth taking home, those would be that studying covariate shift on X-rays is hard because of the covariate shift. Pneumothorax generalization is highly problematic, with exposure fix emerging as the dominant and most influential factor, while the issue of geographical shift remains largely unresolved. That being said, we are strong believers in research with translational value, and proof of that is having these lessons and methods now actually aiding generalization in real deployments across Europe and Asia. Thank you very much for listening.